We're continuing on in chapter 14, looks like. Get everybody in here, hopefully. Okay, so we've been talking about chapter 14, which is acids and bases. We just barely got into it, I think, last time. So I think this is sort of where we were at. So we sort of talked a little bit about naming of acids, in particular, kind of a review, hopefully, for you. Again, just a reminder that, we will come across a lot of acids in this chapter, a lot of bases too. So it's good to know the names because in a lot of problems, they will maybe just give you the name and you need to know the formula. Formula is going to help you obviously write the proper equation that you might need to do. So, it's really important to remember how to do that. Again, as we talked about, it really all revolves around oxygen. If there's no oxygen, those are your acids that start with hydro and end with ic, like HCl. It's hydrochloric acid. If it does have oxygen, it typically will have one of those polyatomic ions in it. And if the polyatomic ion ends in ATE, 8, the acid will be something ic acid, like HNO3 is nitric acid. If the polyatomic ion ends in ITE, then the acid will end in OUS, so like nitrous acid, which is HNO2. So again, there's going to be a lot of problems and stuff where they won't necessarily give you the formula for the acid, may just give it to you in words. So, sort of important to remember how to do that. Good news is, as we talked about, sort of bases, are usually just kind of named like we normally name things. A lot of them do have hydroxide in them. Not 100% have hydroxide, but a lot of them do. All right, so we'll continue on at this point. So, sort of a basic definition of an acid is the one that was done sort of by Arrhenius. He did a lot of work with electrolytes. And if you remember what electrolytes are, those are really solutions that break apart into ions. They help conduct electricity in solution. And he basically defined an acid as something that's able to produce H plus or H3O plus. And that's one important sort of thing that we see with acid and base chapter is when we're dealing with acids, kind of H plus, which is sometimes referred to as the hydrogen ion, obviously. If I spell it right. There we go. Also known as a proton, as we will see in a second. It's known as a proton, right? If you remember, hydrogen has one proton, it has one electron, it does not have a neutron. So when it becomes positively charged, it loses an electron and thus becomes a proton at that point. H3O plus is the hydronium ion, and that is a polyatomic ion. That's the hydronium ion. Hydronium ion, H plus, they are basically interchangeable. So in formulas, equations, you'll sometimes see H plus used. You will also sometimes see H3O plus. They are essentially equal to each other here when we're talking about acids. And really the main difference in terms of whether or not you might get H3O plus or you might get H plus, it really has to actually do with water in the equation. So if we look at this right here, this reaction that we see, this is hydrochloric acid. And remember that typically we do see the aqueous symbol next to it, which indicates that it is an acid. And this is really not necessarily a reaction in the sense of necessarily two things reacting like you might think about it, but it's basically hydrogen gas sort of dissolving in water, and it will make H3O plus and Cl minus. So because we have water in the equation here, we will generate that H3O plus, and we could just as easily write sort of this acid dissociated in water by just simply taking the HCl and breaking it apart into H plus and Cl minus. So here we didn't include water in the equation and we got H plus. This H plus and that H3O plus, basically the same thing. It's basically indicating that the acid basically has given up its H plus in solution. The reality is, in really what's happening is this sort of reaction here, but probably 9 times out of 10, and I personally usually will not write water in the acid when it dissociates. A lot of people will write just a dissociation of this acid like this. So the aqueous sort of stands for the water part of it, and that's why it's sort of not included. So if you include with your acid reaction sort of water in it, of it sort of dissociating, really just breaking apart, you will generate that H3O plus perfectly fine. And again, I'll do it probably like the bottom here, just writing the HCl that breaks apart into H plus and Cl minus, also perfectly fine to represent what's happening with that acid. So we will sometimes see H plus, we'll sometimes see H3O plus, and again, basically representing the same thing here. And the real definition of an acid is really just that when you look on the product side of the arrow, you see H plus, or you see H3O plus that has been formed. And that's basically your definition of this is an acid, sort of acidic conditions probably happening in that solution when you see that on the product side. Now, he defined a base as really something that's able to produce water, OH minus, which is hydroxide. OH minus is hydroxide. OH is sort of a base. And in this particular case, we do have water involved. And usually when we do write reactions for bases, it's a good idea to include the water because people have a very hard time of figuring out sort of what is that base reacting with, especially a base such as this one. So NH3, which is ammonia, that is actually a base. It's a weak base. We'll talk a little bit more about that in a sec, but it's actually a weak base. And one thing that you do see in it is it does not have actually hydroxide in its formula, but it's able to actually react with water here. And basically it will pick up an H plus. And when it does so, it's able to generate that OH minus on the product side and going to make this a base. So this is also a very good example that, not all bases actually have OH minus in the formula. Some do not. But really your definition of a sort of a base is the ability to produce hydroxide there on the product side, OH minus. A lot of strong bases, like we maybe talked about previously, something like NaOH, OH, KOH, sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide. If you sort of look on the periodic table there in group 2 and 1, you kind of go from like sodium to potassium, go to the right to calcium and down. Those are a lot of your strong bases. Those are a lot of the strong bases that also contain hydroxide in the formula. And that's where we do see a lot of strong bases. As I might have mentioned last time, group 1 is the alkali metals. Group 2 on the periodic table is the alkaline earth metals. If you're not familiar with this terminology, alkaline, that pretty much means basic. So that's where a lot of strong bases come from. Your alkali earth metals, your alkaline earth metals, your alkali metals there, group 1 and 2. But as we will see definitely in this chapter and other chapters, not all bases will have that hydroxide in it. Any questions on that there? Now, this is a good sort of definition of acid and bases, but a more general definition sort of came about after that, and that was one that was done by Bronsted-Lowry. The Bronsted-Lowry definition, which is oftentimes what we sort of think about in terms of acid and bases and their definitions. Bronsted-Lowry definition of an acid is a proton donor. So it is not just the H, but it is the H plus part of it. The plus will affect the charge on things, so that's important to keep in mind. So our Bronsted-Lowry acid is something that will basically give away an H plus. The Bronsted-Lowry base is something that will basically accept the H plus. So if we look at that sort of ammonia reaction there with our NH3, again, what is essentially happening is the H2O here is going to donate the H plus over to the NH3. When it does that, it actually creates a partner on the other side, which is NH4 plus. And there is a relationship in a Bronsted-Lowry, which is the base on one side, its partner on the other side is what is known as the conjugate acid. So those two things are related to each other, and they're really partners. Now, Bronsted-Lowry base is a proton acceptor. So that is what we see here. I guess I should have talked about that definition there first. So Bronsted-Lowry base, a proton acceptor. So here the NH3 is accepting that H plus, making it the base. While in the case of water, because it is the one donating its H plus, it is a acid. And what we get over here is the water, which is the acid. It also has a partner on the other side, which is the conjugate base. And again, when it loses that H plus, not just the H, but the charge also changes. So when you lose a positive, you become one more negative, which is why we end up with OH minus in this case. So we lose the H from the H2O, which leaves me as an O and an H. And we had no charge, lose a positive, become negative. So this is the Bronsted-Lowry definition of acid and bases. This is what we oftentimes think about and talk about a lot in terms of acid and bases. And it's really good for a definition of an acid and base, obviously a base here that does not contain OH minus, but able to produce OH minus over here, making it a base. So what is sort of the relationship between these things? Well, my base on one side and my acid on conjugate acid on the other side, the only difference is one more H plus as you go from one to the other. Now, the relationship between my acid on the reactant side and my conjugate base, we'll go this way, over here, on the product side is we go from H2O to OH minus, and that is one less H plus. And the only thing that is the difference between both of them is an H plus. And it is only one H plus, which is really the important part. So in order for something to be what is sometimes considered an acid base conjugate pair, the only difference you could have between those two things is one H plus. So if you have a difference that is more than one H plus, they are not related to each other. They are not pairs to each other. It has to be just one H plus. And that's really because what happens is basically we're transferring just one H plus here at a time. So one H plus at a time in order for those guys to be pairs. So also on the left-hand side of the arrow, where you have your reactants, that is where you find your regular acid and bases. On the right-hand side, which is your products, that is where you find your conjugate acids and your conjugate bases. So those are always the sides where you find those things. Any questions on that there? Okay. All right. Water as well can actually go through autoionization, where basically it is reacting with itself. So one water is going to act as the acid, one water is going to act as the base, and we're going to get that H plus that basically occurs being transferred from one to the next. So if that's our acid, again, the relationship between these two guys, acid on one side, conjugate base on the other, difference is only one H plus. If we go the other way, our base here and its partner on the other side, conjugate acid, again, only one H plus difference, one more in that particular case. Now, water here, as you see, one's acting as acid, one's acting as a base. There are certain things that can act either as an acid or a base, and those things are what are known as being amphoteric. So amphoteric substances are things that have the ability to act in both sort of directions. Could either act as an acid in certain situations, can act as a base in other situations as well. So this relationship between water is an important one. We'll see it here in just a second, but let's take a look at an example here. So take a second here and try to determine which one of these are acid conjugate base pairs and see what you come up with. We have HCl and OCl minus. I don't know why books always write it like that. By the way, that's the same as ClO minus, which is hyperchlorite. So really, when we look at these two things, again, the difference is definitely an H plus, but there's also a difference of that oxygen. This one obviously doesn't have oxygen. This one does have oxygen. So this would not be a pair. Again, although there is a difference of one H plus, it is also a difference of an oxygen, so they would not be pairs. Now, H2SO4 and SO4 2 minus, these two guys are not pairs either. The difference here is actually two H pluses, which does not make them a pair in this particular case. Although you may be tempted to say that they are a pair because obviously they are related to each other. They actually would not be a pair in this case. And that's really because when we lose H pluses, they actually do come off one at a time. So if we had something like sulfuric acid, which is what this is, the first thing that would happen is it would lose one H plus. And the next thing that would happen is that second guy there would then lose one more H plus. So when we look at this in terms of pairs, this one and this guy, they are actually pairs. This guy here, which was the product of the first guy, and the one that we see here, which is SO4 2 minus, these guys would also be pairs. But going from here all the way over to here, they would not be pairs because, again, that's basically a two-step process. We lost two H pluses along the way. So they are still related to each other. They really all come from the same guy, but they are not considered conjugate acid base pairs because there is more than one H plus in terms of the difference. Any questions on that there? Okay, so when we look at NH4 plus and NH3, the difference here is one H plus. So that is a winner there. Again, you could look at it one of two ways. You can either take the H plus off of this guy, take the H off, you're left with NH3. When you take off the plus, you become one more negative. So plus one minus one, you end up with NH3. Or you can put the H plus onto the NH3 and you'll end up with NH4 plus. So this guy is good. We have H3O plus and OH minus. Again, you may be tempted here to say that it is a pair, but it is definitely more than one H plus. It's two H pluses in this case difference, which is not so good. So this guy would not be it. Again, actually, water here would be the one that kind of joins both of them in terms of pairs. And then obviously none of the above would be wrong. So it looks like number 3 is our only conjugate acid base pair. Any questions on those? Really, you know, your option is H plus, and really the big decision for most people is, should I put it on or should I take the H plus off? So sometimes it's good to think about what we talked about earlier in terms of the relationships of things. So if you remember, we have acid and base on our reactant side. We have our conjugate acid and our conjugate base on our product side. And then remember, the relationship is acid on one side, conjugate base on the other, base on one side, conjugate acid on the other side. So in this case, we're looking for the conjugate acid, which would be this guy. So what that tells us is what we are looking at is a base. And again, in a lot of problems, they won't be this nice and tell you these are bases. So a lot of times they won't give you that information. So if you just kind of think about it backwards and go, okay, I know I'm starting with a base. Definition of a base is basically a proton acceptor, which means that it actually should gain an H plus. So you should put an H plus on that, and you'll end up with C6H5 NH. And it's very simply just add one more H to the end. It gives me NH3. And we had no charge, and we're adding a plus. So we become plus there. So that looks like number 2 might be a winner on the choice there. Question on that one. So let's try just one more here. Let's say we had HCO3 minus. Why don't you write the conjugate base for that? And why don't you write the conjugate acid for that guy? So take a second and write the, so using the sort of the same logic, we'll start with the conjugate acid here. So if I'm looking for the conjugate acid, just like we did before, again, thinking backwards, that means in this particular case, it's going to act as a base, which means it's going to accept it, and its partner would be H2CO3. Now, if we're looking for the conjugate base, again, looking backwards, if we have the conjugate base, its partner on the other side would be an acid, which means in this particular case, the acid should donate the H plus. And when it donates the H plus, we will lose the H off of that and become CO3 2 minus. Any questions on that? This again is another example of an amphoteric substance. Amphoteric substance, again, as I mentioned before, could act either as an acid or a base. A lot of amphoteric substances will sort of look like this. They'll have like an H, they'll have a charge. So a lot of those guys that have like an H and a charge, like we saw with HSO4 minus when we were talking about the sulfuric acid one in just a minute ago, again, also could act as sort of a amphoteric, again, having that H and also a charge. So very common sort of guys that have that ability to go both ways. Any questions on that there? Okay.
Yeah, I have a question. So I'm a little bit confused still. So when we're going to an acid, we're gaining a hydrogen plus, but then when we're going to base, we're losing the hydrogen. Is that?
Yeah. So when you're going from, when you're going from really a base on the left-hand side to its partner on the right-hand side, which is the conjugate acid, it is basically going to be gaining one more H plus. So as we go from our base to our conjugate acid, like in this situation here, it basically was plus an H plus, right? And that's going from left-hand side to right-hand side. When you're going from your acid, which is on the left-hand side, to your conjugate base, it's going to lose an H plus, which is what we see coming this way, going minus an H plus. Yeah. And really is from that definition. So it's really important. There is a difference when we talk about, an acid and a conjugate acid. So an acid itself will actually lose an H plus. And when you're just talking about just a regular acid, if you will, in that sense, an acid will always be found on the reactant side, left-hand side of the arrow, and that's always going to lose it. Now, when you're talking about the conjugate acid, that actually is coming from really the base on the left-hand side. And that's going to be the guy that's going to really receive the H plus and gain the H plus. So when we talk about acid and conjugate acid, they really do sort of represent a little different things in that sense. Just like when we talk about the base and the conjugate base, they represent different things. So easy way to usually remember it is, like I mentioned, just kind of if you're just trying to identify what the acid or base is, there's regular sort of acid and base. They should be found on the left-hand side of the arrow. Really, those partners to those guys will be what are going to be the conjugate acid and conjugate bases, which are going to be found on the opposite side of the arrow, the product side. And that's how, on one side the acid is losing it, but the conjugate acid on the other side is gaining it, because really the conjugate acid is coming from the base, which is accepting the H plus. Other questions on that? Okay. Other questions on conjugate acid, bases, pairs, you need to obviously be able to, write these formulas and stuff like that. The good news is all you have to remember is H plus, and the hard part is knowing should you put it on or take it off. And again, just remembering sort of these relationships here, will help you identify, hopefully working backwards what you should do. Again, a lot of problems, they won't give you this part, like, hey, you're looking at these are all bases. So you won't, you also oftentimes have that information given to you. Okay, then let's talk a little bit more then about water and the ion product of water. So water really reacts with itself. It basically does set up an equilibrium. And if we did our products over our reactants, just like we talked about in a previous chapter, we would have our H plus and OH minus. And since water is a liquid, just like in a regular equilibrium, we would not include it. So what that gives us is really what is referred to as Kw. And Kw is really the concentration of H plus times the concentration of OH minus. And as we will see in just a second, it really equals 1 times 10 to the minus 14 at 25 degrees Celsius. So this is really the ion product of water, or the Kw is usually referred to. This is again an equation or a formula where you will oftentimes see as well Kw equals H3O plus and OH minus. Again, the H3O plus and the H plus are pretty much identical to each other. They're the same thing. I personally use H plus a lot. Sometimes books and stuff like that will use H3O plus, but again, pretty interchangeable. So anywhere in the formula, anywhere in the reaction where you see H plus or H3O plus, you basically can interchange each other. We could use this, and when we talk about the concentration, we're usually talking about molarity here. We could use this to determine whether or not a solution is acidic, basic, or neutral by comparing those values. So if we calculate the H plus concentration and it's equal to the OH minus concentration, which by the way means they both will have a value of 1 times 10 to the minus 7, it will be a neutral solution. If you calculate the H plus concentration and it's larger than the OH minus concentration, the acid part is larger than the base part, it will be acidic. If you calculate the H plus concentration and it's less than the OH minus, so really the OH minus is larger, so the base part is larger than the acid part, that will be basic. And again, basically by rearranging this equation or formula, it's really the same calculation regardless of which one you're given. If I write it right, you're basically going to take 1 times 10 to the minus 14 divided by the concentration that was given to you. And let's write it over here. It's going to be the exact same calculation. So you then can compare both of those and see which one ever is larger or if they're equal to each other. And you'll be able to determine is it acidic, basic, or neutral. So this chapter and every chapter we do, just a friendly reminder that when you put a number in scientific notation, make sure that you use your exponent button, which in most calculators looks like one of these two buttons. You might even have one of those new calculators that actually does have a button like this for exponents. If you have either of these buttons, when you put in something like 1 times 10 to the minus 14, you would type in 1, you would hit your exponent button. It will probably put a 1 and an E there. That E stands for the times 10 part, which means you should not hit the multiplication button or inverse log or anything weird like that. You then would hit your negative button, which looks like this, and 14, and it'll be negative 14. May even pop up some zeros when you do that, like exponent button, and then you'll get the negative 14. If you have this button here on some of the newer calculators, you need to use parentheses. So you need to put parentheses around every number you put in there in scientific notation. Otherwise, you will get the wrong answer in most cases. So also a reminder that, again, negative button, most calculators looks like this, looks like this. Don't use your subtract button or you'll get the wrong answer. So Very common. People have a very difficult time. Again, make sure that you do use your exponent button. Otherwise, you will find yourself off. The way you'll know if you're maybe off is you'll oftentimes see the front part of the number looks good, but that exponent part is like off by a factor of 1 or 2 or something like that. So, if you get an answer like 2.5 times 10 to the minus 6, and the real answer is like 2.5 times 10 to the minus 5, it's probably the way you're punching it into your calculator. So keep that in mind as you go through these. If you have any trouble, make sure you at some point talk to me about it. We'll try to figure it out on your calculator. But if you have kind of that newer button on the bottom, my experience with that is a lot of times you got to put parentheses around every single number. Otherwise, your calculator does some weird math. So why don't we try one to make sure everybody's calculator is working. So take a second here. What is the OH minus here? If we have a 1.3 HCl concentration, and also determine, is it acidic, basic, or neutral? So take a second and see what you come up with. 2H plus and Cl minus. And if this concentration is 1.3 molar, it is a 1-to-1 relationship between the H plus, which is what we're really looking for here. And we know that the H plus concentration would also be 1.3 molar. So would the Cl minus, but not really important here. We could use our Kw, which is our H plus times our OH minus, and that equals 1 times 10 to the minus 14. And again, that 1 times 10 to the minus 14 is a number you probably will use 99.9% of the time, but you should remember that this is still a K value, which means if the temperature is really not 25 degrees Celsius, there actually will be a different value for this, but probably 99.9 times that 1 times 10 to the minus 14 is what you're going to have. So if we rearrange this and solve for the OH minus, that's going to give us 1 times 10 to the minus 14 divided by 1.3 molar. And if we do that, maybe 7.7 times 10 to the minus 15, that would be molarity here. And that would be our hydroxide concentration. Any questions on that there? Now, what we want to know, is it acidic, basic, or neutral? And we need to compare the two. So obviously, when we compare the 1.3 minus 15, we know that the OH minus is less than the H plus concentration. That would tell us obviously it's acidic, and we would hope it would be acidic since it is hydrochloric acid, right? So we would hopefully expect that that should be the case. Any questions on that there? The next one. So next one should be hopefully this one here. And it is 1.2 times 10 to the minus 6. We're looking for the OH minus. And again, as we talked about, it's pretty much the same calculation no matter which one they give you. So we're going to take 1 times 10 to the minus 14. Make sure we take our exponent button and put it in that way. 1.2 times 10 to the minus 6. And if you do all that good stuff, you should get something like 8.3 times 10 to the minus 9. Again, it should be molar because it is a concentration. If you don't have your calculator in scientific notation, you might end up with a bunch of zeros there, probably 8 of them. And an 8 at the end because you ran out of room. So that's, if you put it into scientific notation on your calculator, that's how you get to the 8.3 times 10 to the minus 9. My calculator runs out of room if it's not in scientific notation at that point. First off, any questions on the number there? The next thing we want to know is it acidic, basic, or neutral? So as we talked about before, we have our H plus concentration. That is 1.2 times 10 to the minus 6. We have our OH minus concentration, which is 8.3 times 10 to the minus 9. And what we see is the H plus concentration is larger than the OH minus concentration, which means this guy should be acidic. A reminder about exponents and negative exponents. This is -6. This is -9. When you have a negative exponent, the smaller exponent is actually the larger number, because -6 means we're only going 6 places this way with zeros. -9 means we're going more places to the left with zeros, making it a smaller number. So sometimes people go, hey, that's a 9 and that's a 6. Shouldn't this one be bigger? But it's not. Again, if you turn it into decimal form like here, we see we have a lot more zeros than we would if we turned this guy into decimals as well. Question on that calculation there. So again, hopefully you're punching in with your exponent button. You're not having issues with that. Again, if you are having issues with that, is probably the way you're punching in. So for example, if you got a number like 8.3 times 10 to the -8 or something like that, or to -10, it's probably the way you're punching it in. And again, if you need help with that, make sure you do ask. Any questions on KW there? And again, here we use H plus, but H3O plus, same thing. This could have said H3O plus and it would come out the same. So this is one way that we could figure out whether or not a solution is acidic, basic, or neutral by comparing really the H plus concentration or the OH minus concentration. And really all we're doing is in a solution, there's a certain amount of H plus is floating around, a certain amount of OH minus is floating around. We're just trying to see which one of those guys floating around in that solution is larger. Another more convenient way that we oftentimes think about acidity is by looking at pH. And pH is equal to minus the log of the H plus concentration. The pH scale runs from 0 to 7 to 14. Below 7 to 0 is acidic. Above 7 to 14 is basic. And really dead on there, 7 is neutral. 7 is sort of our center point. So as we go from 7 towards 0, where you're becoming more acidic. As you go from 7 towards 14, you're becoming more basic. And to calculate the pH is minus the log of the H plus. Again, just like all the other formulas here in acid and bases, you will also sometimes see it written minus the log H3O plus, same deal, same thing. So while we're talking about calculators a little bit, let's talk about how you punch this in on calculators. If you have a display calculator, you punch it in exactly the way it's written. You hit the negative button, not the subtract. You hit the log button, then you type in your concentration in terms of exponents using the exponent button. If you have a non-display calculator, this one and all the rest of them, you need to go backwards, which means you need to start with the number, hit the log, and then hit the negative. If you're not sure if you have a display or non-display calculator, simply hit the log button. If you hit the log button and it says log, congratulations, you have a display calculator. If it says error, congratulations, you have a non-display calculator. So that's a good way you could recognize, which type you have. So if you have a display calculator, this one and all the rest of them will see straight across the way it's written. If you have a non-display, you do need to go backwards in terms of how you punch those things in. We could use the pH scale here to help us decide whether or not something's acidic, basic, or neutral by the pH value. So again, here, as I just mentioned, if the solution is neutral, that means that the H plus concentration will equal the OH minus concentration. And why a neutral solution is pH of 7? It's because the concentration would be 1 times 10 to the minus 7, which would give you a pH of 7 in this particular case. So if it's just above 7, it's slightly basic. If it's just below 7, slightly acidic. It will go for here to make it simple. It needs to be dead on 7 to be neutral. Again, if it's slightly higher or less, we'll consider it slightly acidic or slightly basic in this particular case. Some people will give a little window on both sides, but just to keep it really what it should be. If it's 7, it's neutral. If it's not, it's either, again, slightly acidic or basic if it's in that area. So let's talk about an important thing in terms of relationships here with pH. As the pH goes up, the H plus concentration goes down. And there is an important relationship between H plus concentration and OH minus concentration. And the relationship is as one goes up, the other goes down, and vice versa. Obviously, as the H plus concentration goes down, the OH minus concentration will go up. So as the H plus concentration goes up, the pH will go down. And as we see on the bottom there, the pH will go up if the H plus concentration goes down. So those are some important relationships. Let's talk about another important thing, which is everybody's favorite thing, which is sig figs and pH type values. So when we're calculating the pH and we're looking to try to do the right number of sig figs and all that good stuff, the pH value or value like that, doesn't necessarily be pH, but value like the pH should have the same number of decimal places as the concentration has significant figures. So how many decimal places you take your pH value, pOH value, a value basically like a pH, you take it to however many decimal places is, I said that was a lot of S's, I think, at the end of that, how many decimal places there are that's equal to the number of significant figures in the concentration. So we're going from significant figures in the concentration to decimal places in the pH. And it works the opposite the same way. If you have a pH and you go back to concentration, it's going from decimal places to significant figures in the concentration. So just to make sure, again, everybody's calculator works correctly. What is the pH if the solution has an H plus concentration? We'll go 1 times 10 to the minus 5 molar. So take a second, calculate that, and think about what the proper pH, how it should be reported, you get. So take a second and calculate that, and we'll talk about what the answer pH would equal minus the log of 1.0 times 10 to minus 5. And when you do that on your calculator, it spit out to you 5. Hopefully, we'll start with just make sure you got the right number there. So again, if you have a display calculator, negative button, log button, 1 exponent button, negative button, and 5. And if you have a non-display calculator, 1 exponent button, negative button, and 5, log button, and then negative button going backwards. First off, any questions on how to get to the 5? So at this point, we could report 5. We could go 5.0, go 5.00, 5.000. Which one is the proper way to report the answer here? Hopefully you chose this guy right here, 5.00. When we look at this number here, which is the concentration, concentration has 2 significant figures. 2 significant figures does not give us 2 significant figures on the pH. It gives us 2 decimal places. So significant figures to decimal places. So 5.00 should be the correct way to record that. Question on that? Now, again, we're going to talk about how to go backwards the other way. So if we're going backwards the other way, if you started with a pH of 5.00, you should end up with a concentration like 1.0 times 10 minus 5, which is 2 significant figures. So it works going both ways. Sig figs to decimal going to pH, decimal to sig figs going back to concentration. Any questions on that? That obviously would also be an acidic solution at 5.0 there, pH. All right. So that is the pH scale as we see here on the left, and some things on the pH scale. Obviously, we have sodium hydroxide, which is a strong base up there in the basic range. On the bottom range there, we have HCl, which is a strong acid. We have things like stomach acid and lemon and vinegar, which like acetic acid and stuff like that, which is in the acidic range. Ammonia, which is a cleaner there, is also basic. We also see pure water is a pH of 7. If you take like tap water or something that's not maybe pure water, or water that's been sitting out for a while, people are often surprised the pH is like in this range. It's oftentimes acidic if you have a water that's been sitting out for a long period of time. And that's because when water is sitting out for a long period of time, it picks up some CO2 in the air and makes some carbonic acid, raising the H plus concentration, bringing the pH down. So sometimes you do critical experiments, maybe you've done it in the past. A lot of times during titration, sometimes they'll have you boil the water before you kind of make your solutions. When you boil the water, you're removing a lot of that CO2 that's gone in there, and that's going to bring the pH sort of back up. But sometimes people are surprised, you know, sort of acidic a lot of times, especially if the water's been sitting out. Now, there is another scale that's similar to the pH scale, and that is the POH scale. And the POH is equal to minus the log of the OH minus concentration. The name actually tells you what you need. POH means you need the OH minus concentration. pH, like we just were talking about, you need the H plus concentration, right? So kind of the name tells you what you need. Why are these two numbers good? These two numbers are good because there's a nice relationship between the two. If you take the pH and you add it to the POH, it equals 14, which means in certain cases, you can kind of quickly calculate one or the other if you're given OH minus or H plus concentration. So it allows you to do some other calculations. It should be noted that when you're trying to determine whether or not the solution is acidic, basic, or neutral, you probably should be looking at the pH value, because that is the scale most people have in their head. The POH runs opposite of the pH scale, which means if you have a low pH, you have a high POH, and vice versa. If you have a high pH, you have a low POH. So you do run opposite of each other. By the way, when you're asked that question, is it acidic, basic, or neutral? There is only one answer. It cannot be acidic and basic at the same time. I've never really had anybody do acidic, basic, and neutral when asked that question, but I've had people do acidic and basic at the same time. And that's because they look at like the pH value and go, oh, it's above 7, it's basic. Then they look at the POH value and go, oh, it's less than 7, it's acidic. So it can't be both. It's one of those things, and they actually both tell you the same thing. So don't be the person that does that. While we're talking about some things here, we could also, if you are given the pH value, you could get the H plus concentration from that. The H plus concentration is the inverse log of the minus pH. So usually when you go inverse log on your calculator, it pops up a 10 and a caret minus pH. Same thing if you're given the POH, you could get the OH minus concentration from that by taking the inverse log, same calculation, of the minus POH. So those are two other things that can oftentimes be easier. These guys will also allow you maybe not to have to use KW. It gives you a couple different options as to how to solve some of these guys. So these things here, KW, pH equation, POH equation, pH plus POH, the calculating the OH minus concentration from the pH and calculating the H plus from the pH there, are all things that you do need to know. Any questions on any of those there? Also, why you want to make sure you're using your exponent button, because obviously if you're using like shift log, inverse log to do exponents, and you need to do inverse log to do the calculation, you're going to run into trouble for yourself. Any questions on any of those there? All right, so why don't we try one here. Let's take a look here, see what we got. Perfect. So the pH of rainwater is collected. It has a pH of 4.82. What is the H plus? Why don't we do everything? What is the OH minus concentration here? What is the POH here? And is it acidic, basic, or neutral? And on the bottom one, we have an OH minus concentration given to us. What is the pH? So in addition to pH, why don't we do what is the POH? What is the H plus concentration? And is it acidic, basic, or neutral? All right, so take a couple minutes here and see what you come up with those. We'll compare answers. Hopefully we'll get the same answers. The pH given to me, and one of the things I want to calculate, I asked you to do is the POH. So again, simply we can take the pH plus the POH is equal to 14, which means that my POH would equal 14 minus 4.82. And one answer would then be 9.18 as my POH. I also have the pH given to me, which means I could directly get the H plus concentration from it by taking the inverse log of the minus pH. Don't forget the negative here, otherwise you will get the wrong answer. And again, when you punch that in on most people's calculators, that's usually the top left button there, like the shift button, the second button, the log button, and it usually will hit and put in a 10 and a caret on most people's calculators. Again, you want to then make sure you hit the negative and 4.82. And if you do that, it looks like we'll go with 1.5 times 10 to the minus 5. Here, 2 decimal places gives us 2 significant figures in our answer. So that's why we went to 1.5 on that particular one. And what's left there? That last is left. Is it acidic, basic, or neutral? Again, we want to look only at the pH value, which is 4.82, and that is less than 7, which means it is acidic at that point. Question on any of those numbers there? Okay, then yeah.
Sorry. Yeah, real quick. So for the 1.5 times 10 to the negative 5, I got 1.4. Is that close enough, or am I putting it in wrong?
Maybe, because on my calculator, when I do it, I get like 1.51356. So it should come out pretty similar to yours.
Okay.
It might be in decimal form, like 0.0000151, but you should definitely get something close to that. So maybe double check.
Cool.
Other questions?
And then you got acidic because of the 4.82?
I did. So there's a couple different ways you could kind of do it. But because the pH value was 4.82, that's all you need to look at. And what you probably really should look at in this case, because it's less than 7, so it's acidic. This is a situation where I was talking about just a second ago. Sometimes people look at the 4.82 and go, oh, it's acidic, but then they'll look at the POH and go, oh, it's above 7, it's basic as well, and it's not the case. So you want to always get into habit of looking at the pH value if you have it, because that's usually the scale most people have associated with what's going on here. I didn't do the OH minus concentration, by the way. So OH minus concentration, you could also do the same way. You could do the inverse log of the minus POH. I guess you should put that number in there. And that's going to give me a 10 and a caret minus our 9.18. And if you do that, looks like you get 6.6 to the minus 10. So I'll go this way with it. 6.6 times 10 to the minus 10 molar. as our OH minus concentration. So at this point, you could have also compared the H plus and OH minus concentrations to each other and see what you came up with in terms of which one is larger. You also could have done KW as well, you know, to get the other one, whichever way you want to do it. They all should come out the same. Any other questions on that one there? Okay, so let's just finish up this last one here before we call it for lecture. So in this case, we have the OH minus concentration. So again, if you wanted to, just like we did before, you could go into the H plus concentration by using KW. And that would give us an H plus concentration if we did it that way. Again, making sure to use our exponent buttons here of 4.0 times 10 to the minus 8 molar. We also have the OH minus given to us, which means we could directly calculate the POH, which would be minus the log of the OH minus concentration. And that would be minus the log of 2.5 times 10 to the minus 7. And that's going to give us a 6.60. Again, 2 sig figs, 2 decimal places here for our POH. Now that we have that, we could simply do our pH would be 14 minus our POH. So that's going to give us 14 minus 6.60. Gives us 7.40 as our pH. And I feel like I'm missing one. What am I missing? Anything? No, I got H plus, got the pH and POH. That's everything. So at this point, we want to know, is it acidic, basic, or neutral? It would be slightly basic at this point. Again, just slightly above 7. And that would be considered slightly basic at this point. Also, you could have, if you wanted to, because you had the OH minus concentration, did the inverse log of the minus POH to get the OH minus concentration. And then you could have used KW to get your H plus, or you could have done your pH first and then got it that way. So there's multiple ways you could kind of do some of these problems. They all should come out the same. You know, it's kind of depending on whichever path you choose. Any questions on any of those there?
Professor, isn't it better to find the POH first, or is it safe to assume that temperature is always constant?
Yeah, so like I said before, you could do any one first. So you could have, if you were just going to answer the original question, which was, you know, what is the pH? You probably would calculate the POH, subtract 14, and be done. So that's perfectly fine to do that way. And like I mentioned before, even though, again, none of these mention anything about temperature, it's safe to assume that the temperature is 25 degrees Celsius, and it's safe to assume probably that, you know, the KW value would be 1 times 10 to the minus 14. Again, if it's not really 25 degrees Celsius and 1 times 10 to the minus 14, they definitely will in a problem mention the temperature that's not going to be 25, or again, you know, kind of give you that different version of KW to use. So, and again, it's probably it's probably a rare occasion in a lot of situations, but it definitely can happen. And I've seen it in a lot of like textbook back of the chapter type problems and stuff like that. There's sometimes pop up, and it throws people for a loop sometimes, because they have sort of that 1 times 10 to minus 14 is always the number to use. And like I said, 99.9% it is the number to use, but there is that little chance that, you know, if the temperature is changed, because it technically is a K value, it can change as well. Kind of the same idea as density, although we think of density of water as 1 all the time. Density changes with temperature as well. So, you know, if the temperature is not really 4 degrees Celsius, technically the density is probably not 1 as well. So kind of the same idea as that. But for us, and like I said, most of the time, 1 times 10 minus 14, pretty safe to not think too much about it and just go with it. Other questions?
Thank you.
Yep. Okay, so we'll lay it up here for lecture. A reminder, we are going to have a quiz on Monday on chapter 13. I think what we're going to do is we're going to have lecture like normal. I think we'll take the quiz at the beginning of lab, And then we'll kind of take a little break and then start lab a little bit later and do the lab, after the quiz. So as of now, unless something changes, and I'll let you know, but as of now, we'll have lecture like normal, whole lecture. And then at the start of lab around 1 o'clock, we'll take the quiz. And then you'll have whatever, 30 minutes, 35 minutes maybe to take it. And then, maybe 10 minutes after that. So probably around 2-ish, we'll start lab and do the lab that's scheduled for Monday. Any questions on that?
You know, we're gonna do Proctorio, or are we gonna log into the lab and be on Zoom and then take the exam and you proctor through Zoom?
Yeah. The honest answer is I'm still not sure, but I think I might be leaning for this first one. We might do it through Proctorial, and then just come into the lab meeting like normal at maybe around 2-ish. But so right now I'm leaning towards doing it that way. But if not, then we would obviously do it like the other way, which is no big deal. We just log into our normal lab meeting at 1, and we'll do it that way, and then take a little break and start up the lab. So I'm kind of leaning towards Proctorial maybe for this first one, but I'm not 100% on that either, to be honest with you. And I haven't ran the quiz yet, so I'm not sure how many questions are on it. That's really what Monday morning is for, right? But I imagine like normal, it's probably no more than 3 or 4 questions would be my guess at, kind of the most. And probably problems where you'll need to work out, obviously, and stuff like that.